So this is the last little bit about gas laws, and it's called, what I'm going to talk about are deviations from ideal behavior. That sort of sounds like a something you'd say to a delinquent or something, but another way to look at it is I'm going to talk about real gases. Now, an ideal gas is a gas that conforms to all of the gas laws that we've talked about, okay? And for the most part, all gases are ideal gases, and work with those formulas. But if you push a gas to extreme temperatures or pressures, they no longer conform to those gas laws, and they act as real gases. So here's kind of an example, or a graph that I want to draw, and then I'll explain the graph. On the y-axis, I'm going to graph the pressure times volume. Okay, if you remember from the lab, that was a constant amount. And down here I could just, on the x-axis, graph pressure. And if I was to graph an ideal gas, it would give me a straight line going straight across like that. So a real gas, no, an ideal gas is going to be like that. Alright, a straight line. So this is an ideal gas. What actually happens with real gases is they take a line that looks more something like this and goes up like that. So this would be how real gases behave. Now, it's not really that big of a deal, because for this to start messing up happens to be at what we would say really, really low temperatures and really, really high pressures. So this is the realm of where gases no longer behave ideally, and they start to deviate from those laws that we described. So the thing to remember is low temp and high pressures where things start to get messed up. And I'll kind of give you an example of how that works, or why that works. All right. So let's say I have this little nanotube full of, where'd this blue come from? Get rid of that. Okay. This little nanotube full of just a couple gas particles. Okay. So I got a green one and I got two green ones sitting in there. And this little nanotube of mine has a plunger that I can push, so I can squeeze them. So I can squeeze both these gases from both sides. Okay. So if I push on that little plunger, keep pushing it in and in and in, I'm going to get it smaller and smaller, smaller and smaller volume. All right. So initially, here I go. Okay. This little gas particle in here has kinetic energy, so it's just like, streaming around, and they're bouncing, going, flying all over the place, exerting pressure because they're bouncing off of the side of the container. And now I sit there and, okay, I'm going to squish them. I'm going to push them together. So I squish my plungers down a little bit more. Okay, now all of a sudden, these gases, these two gas particles, they're hitting the side of the container a little more frequently, because I have increased the pressure by decreasing the volume. This is Boyle's law. Decrease volume, increase pressure. Decrease volume, increase pressure. So then I push them again, and everything's working great. Okay, it's behaving as Boyle's law. And just to write what Boyle's law was again, it was pressure times volume is always going to equal some constant amount. Not sure I can't. A and T. There we go. Okay. So pressure times volume is going to equal some constant. So I keep squishing them together, and everything's just working great. The pressure keeps getting bigger, these higher, because these guys are moving around in a smaller volume, and they're just bouncing around going crazy. Now, all of a sudden, I am going to reach a point where everybody is squished so close together that now attractive forces, those forces that get molecules to combine with each other is going to take control. And what's going to happen is they're not going to be looking like separate particles anymore. They're now going to be smacked together and stuck. Well, when that happens, that's going to show a lower volume. So the volume is going to be smaller than would have been predicted because they just took up less space. All right? They're still bouncing around exerting pressure, but the volume just decreased. Now, if I keep squishing them more and more and more, okay, should get higher pressure. Well, at some point now I can't squish them into nothing. I end up where I'm just pushing against these solid little gas particles. Oops, get back here. And now the volume goes really, really high. So that is where on the graph, all right, going back to this area right here, okay, why the deviation was below what ideal gases would be, was due to attractive forces. And those attractive forces are making the gas molecules stick together. And in reality, what that is you're condensing it into a liquid. So, okay, so the volume is less than predicted, so that's why I had a drop in the curve. Now I keep going on the other part of the curve, and I'm talking about this part up here. Now I'm deviating above, my volume is greater than is predicted by ideal gases, and this is due to the actual space gas molecules take up. So this is the volume, the actual volume of molecules, okay, or atoms, but you know, if it's a noble gas, it's an atom. But it's kind of, you got to kind of think about it, but this is what's going on. So basically, right here, this is where things start messing up, and they're messing up because I'm at really, I can mess them up by going really, really cold, or pressing them, pushing them together at really, really high pressures, and they're going to deviate. All right, so try to kind of get this. It's the last thing on gas laws.